Okay, so in this video, we're going to have a little bit of an introduction to chemical reactions. So we're going to be able to identify if a chemical reaction has occurred. We're going to identify the major parts of a chemical equation, including products, reactant, state, and coefficient. We'll be able to count the number of types of each atom in a chemical equation, and we'll also work some on classifying chemical reactions as synthesis, decomposition, single displacement, or double displacement. So that's kind of where we're going to go in this video. So let's get started. Okay, so first and foremost, I wanted to remind you what is a chemical reaction. So chemical reactions are a transformation of one set of atoms or molecules into another set of entirely different chemical identities. So remember, this means you'll have something different at the start than you do at the finish. The chemical formulas at the start will be different than the chemical formulas at the end. And there are many different kinds of chemical reactions, so we'll add them to our toolbox throughout the semester, but this chapter is just meant to get you reading and understanding the basics of chemical reactions. So I want you to be able to look at a chemical equation, be able to read it, understand it, love it, all that good stuff. So down here, I have a picture depicting a chemical reaction. This is actually water decomposing into O2, oxygen, and H2 molecules. So we can see that on the left we have something entirely different. We have one red oxygen molecule with two white hydrogen molecule or atoms, on the left hand side to make up that water molecule. These are water, and then over here we have the hydrogen and oxygen molecules, so O2 gas and H2 gas. Remember, they're some of our diatomic gases, so they form those molecules of two. So that's kind of what we're looking at here. Let's keep going. So how do we even know if a chemical reaction has occurred? So we had the evidence of chemical reactions lab. So this was lab 2. So we saw temperature change, we saw color change, we saw precipitation of a solid, we saw evolution of a gas. So these are all evidence that a chemical reaction has occurred. However, you have to be careful because if the color lightens, it can indicate dilution rather than an actual chemical reaction. So you have to be careful. Are you just seeing the color get lighter because it's getting more dilute or less strong? Or is the color change an actual change in color? Because if it's a change in color, it's a chemical reaction. But you got to be careful a little bit there. If the color lightens, it can indicate dilution. So for example, in the post lab for lab 2, it asked a question about if you put water into coffee, is it a chemical reaction or is it a physical change? It's just a physical change. All we did was add a little bit of water to the coffee. Yes, the color of the coffee got lighter. However, all that is basically a cafe Americano. If you went to a coffee shop or something, you still know you're getting coffee in the end. You're just getting coffee mixed with water. So it's just a mixture. It's not actually a chemical reaction. So that's kind of one little tricky thing you got to be careful of with evidence of chemical reactions. But otherwise, if it literally changes to a different color, of course, chemical reaction. But if the color lightens, it might be dilution. So remember again, how do we know? Well, we've got different molecules at the start of the process than we do at the end of the process. And my goal is for you guys to be able to either we're looking at the chemical reaction, we're looking at the chemical equation, we're looking at the ball and stick model, the space filling model, I don't know, a list of atoms, so that you can determine if the left-hand side of the chemical equation or the left-hand side of the picture or the start of the reaction matches the right-hand side or not. So my goal is that by the time we've talked about chemical reactions, you can definitely look at something and say, chemical reaction, not a chemical reaction. So I would like you to think a little bit about this picture here. Which of these two shows a chemical reaction? Go ahead and pause, spend some time thinking about this. So I believe it's the bottom pictures that represent a chemical reaction. So if we're looking at the top image up here, we can see that we have one black carbon atom with two oxygen atoms. These are all CO2 molecules. They're all the same. And then when I look at my end products to the right-hand side here, I see that I have one black carbon atom with 2 red oxygen atoms. So I still have the same connections. I still have the same molecule, same chemical formula, CO2, on the left-hand side and the right-hand side. It just looks like I'm going from the solid state maybe, or maybe the liquid state. I say the solid state because it's carbon dioxide, so we know it goes from solid to gas. That's dry ice. So I would say that's probably solid carbon dioxide going to gaseous carbon dioxide. When we're looking at the bottom picture here, I say this one better represents a chemical reaction because when I look at the left-hand side, I've got some hydrocarbons. So I've got some molecules that are made of just carbon and hydrogen. We call those hydrocarbons. So that'd be like propane, butane, methane, all the anes, all those natural gases. These are what... they're hydrocarbons. So we only see carbon and hydrogen on the left-hand side in our picture. But on the right-hand side, we can see that something's happened. We've somehow introduced some oxygen in here. We've got some red atoms. So now we see we have carbon dioxide, again, that same molecule that's up here. And we also have water, our best friend. So our red oxygen, 2 hydrogens, water. So which of these shows a chemical reaction? This one down here actually shows me that I have something different at the beginning than I do at the end, whereas over here I have the same chemical molecules at the beginning and end. So, okay, so how do we actually read a chemical equation? We've talked about, has a reaction occurred? I'm talking about chemical equations. What in the heck? Let's talk about how to read a chemical equation. So, you're going to have kind of some stuff on the left-hand side separated by an arrow, some stuff on the right-hand side. So in that case, the left-hand side of the arrow represents your reactants. So the left-hand side are the reactants or your starting materials, and the right-hand side are your products or what are left at the end. So it's kind of like time moves following the arrow. So we're going from CH4 and O2 to CO2 and H2O. So time's kind of moving from the left-hand side to the right-hand side. Really what it's doing is it's following time according to the direction that the arrow points. Later in the semester, we might see a situation where we have arrows pointing in both directions where the reaction's reversible. But for right now, we're going to think about it from going from the left-hand side to the right-hand side. So from the reactants to the products, left to right. So, we will find that again, the reactants are separated on the left-hand side, and each different reactant is separated by a plus sign. So here we have CH4, here we have O2. I know that there are 2 different things, and I mean that they're 2 different things because I have this arrow separating the 2 chemical formulas. We also want to indicate the state in which our reaction takes place, solid, liquid, gas, aqueous. So we see all these little G's after all our molecules, our chemical formulas, because that's telling us that we have methane gas reacts with oxygen gas to give us carbon dioxide gas and water as a gas. So we want to know those things because it's going to make a difference. If I were reading this chemical reaction and I wanted to complete it, I would need to know what state things are in to accurately complete the reaction. So, you may see S in parentheses to mean solid. You may see G in parentheses to mean gas. If you ever see L in parentheses, it means it's a pure liquid. So water oftentimes is pretty much one of the only places we'll use the L. Otherwise, almost everything else is aqueous. So that means it's dissolved in water. So if it's a liquid, it may not be just a pure liquid, which is what we use the L to indicate. If it's a solution with water, we use the AQ to indicate that it is an aqueous solution. So, make sure you're putting the state with everything in every instance because it's important, and you will not be indicating exactly what you mean if you do not put the state. So unfortunately, chemical reactions and chemistry in general is one of those things you have to be extremely meticulous about. So it kind of is what it is. So you got to remember there are lots of different parts of our chemical equations here, but it can be very easy to forget and leave off the state. So you got to make sure that the state is there. And then the other really interesting thing that we see here that we have not seen before are these numbers out in front Oh man. We've got a number out in front of our H2O and a number out in front of our O2. What's happening here? Well, coefficients actually change the entire number of copies you have of a molecule. So, here we have 2 whole oxygen molecules. And over here we have 2 whole water molecules. So this is telling us that 1 methane molecule reacts with 2 oxygen molecules to make 1 carbon dioxide molecule and 2 water molecules. So if we just say CH4 plus O2 gives us CO2 and H2O, we aren't actually really representing what's happening in real life, because that's not what's happening. What's happening is that methane is going to react with 2 oxygen molecules. So our methane is going to react with 2 oxygen molecules, not just 1, because we want to make sure that we're always indicating that our chemical reactions follow our favorite topic, the law of conservation of mass. So, remember, the law of conservation of mass is back, as always. So matter is neither created nor destroyed in a chemical reaction, so our chemical equations have to represent this so that they are accurately representing the chemistry that we're doing. So chemical equations must be what we call balanced. That's what we call adding the coefficients in. When we add those coefficients in, we're balancing the equation so that we can determine that we have the same number of things on the left-hand side as we do on the right-hand side. So we have to have the same amount of each type of atom, the same number of carbons, the same number of hydrogens, the same number of oxygens in the case of our methane and oxygen reaction on the left-hand side as we do carbon, hydrogen, and oxygen on the right-hand side for our products. We got to have the same number of each of those types of atoms. So every chemical equation we write must be balanced to show that the law of conservation of mass holds. I want to be extremely clear at this point. If you do not balance an equation, it will be wrong. I am expecting from here on out that all of your equations will be balanced. Once we get to the point where you have that skill. But I will remind you, however, you have got to make sure it's balanced, and yes, it's incorrect if it's not balanced, okay? So we'll build our skills to get to that point, but for now, we're just going to learn to count each type of atom so that we can later on use that skill to determine if a reaction is balanced. So we're going to learn how to count the number of type of each atom. Then we'll learn to use that information to determine if an equation is already balanced or not. Then, once we know if it's balanced or not, we will use our counting atom skills to determine if they, to determine how to balance them if they're not already balanced. So, that's kind of where we're going here. So we're going to learn how to count the number of types of atoms in a chemical equation. Okay, so we're going to get some practice in counting the number of type of each atom in each of these chemical equations, okay? Remember, the coefficient tells us the entire number of copies of a molecule. So we have to multiply the subscript by the coefficient to get the total number of atoms that we're looking for in the end. So I'm going to go ahead and work through some examples so that you can kind of see how this works, because it's much easier to get a feel of it from doing it rather than just having me try to explain it to you in words. So we want to know how many of each type of atom are present in the reactants and in the products of the first equation there. So this is hydrogen gas reacting with oxygen gas so that it can produce water. So our arrow is here in the center. So remember, the reactants are on the left-hand side and the products are on the right-hand side. So I'm going to first count the number and type of atom in the reactants, and I'm going to count the number and type of each atom in the products. So the first thing I like to do is go through my whole list of reactants and write down everything I have, then go through my whole list of products and write down every type of atom I have. So if I'm looking at the reactants on this equation, I have hydrogen and oxygen. And in the products, it looks like I have hydrogen and oxygen as well. So from here, I'm going to start to count the number of each. So if I'm looking at this, I see that I have two hydrogen molecules. So each hydrogen molecule contains two hydrogen atoms. So if I have two hydrogen molecules, I have four hydrogen atoms, two from each hydrogen molecule. If I'm looking at oxygen, I just have one oxygen molecule. If we do not see anything written in front of our we don't see a coefficient written, we don't see anything written out in front of our chemical formula like this, it counts as 1. Just as everything else in chemistry, we don't write the number 1, so if you do not see a coefficient, it means coefficient of 1. So my oxygen basically has a coefficient of 1, so I have O2 here, so I have one O2 molecule, so I get two oxygen atoms from my one molecule. So I have two oxygen atoms, okay? So in my reactants, I have four hydrogen atoms and two oxygen atoms. Now let's do the products. So if I'm looking at the products, I have two water molecules as my product. So if I want to know how many hydrogens I have, I got to kind of think it through. If I have two water molecules, I have two hydrogens in each water molecule. So I'm getting two hydrogen atoms from each water molecule I have. So therefore, if I have two hydrogen atoms in each molecule, and I have two molecules, I have four hydrogen atoms. Four hydrogen atoms. And then when we're thinking about oxygen, we're thinking, okay, I've got two copies of this water molecule again. I've got two water molecules. So I must get one oxygen from each water molecule. So I have two oxygens. So in this case, each of our atoms has the same number of atoms on the left-hand side as it does on the right-hand side. So we have the same number of hydrogens in the reactants as we do in the products. I'm going to have to get that. Okay, so let's go ahead and work through example number 2. Okay, so let's go ahead and count up the number of types of each atom in the second example. So in this case, we have CaCO3 decomposes into CaO and CO2. So I have calcium in my reactants, I have carbon in my reactants, and I have oxygen in my reactants. I'm going to look at my products. I have calcium in my products. I see eventually that I have carbon in my products and I have oxygen in my products. I generally like to make these lists for every kind of reaction that I'm going to do, but I also like to make sure that for my reactants and for my products that my list is in the same order all the way down. It just is going to make our life much easier anyways. So every time I'm listing this out, I try to keep the elements in the same order if I can. So I'm going to go ahead and count the number of each type of atom in the reactants, remembering that I'm only counting what's on the left-hand side of the arrow. So I see that I have one CaCO3 molecule, so therefore I'm getting one calcium from that, one carbon, and 3 oxygens. So 1 calcium, 1 carbon, 3 oxygens. When I'm looking at the products, I can start to count from the products. So if I'm looking at that, I have 1 calcium. If I look through my equation, I have 1 carbon. However, I still have 3 oxygen atoms. I'm getting 1 oxygen atom from the calcium oxide, and I'm getting 1 or 2 oxygen atoms from the carbon dioxide. So I'm getting 1 here from the calcium oxide and 2 here from the CO2. So I have 3 oxygen atoms in my products as well. So if I'm counting these up, I see that I've got 1 calcium, 1 carbon, 3 oxygens in that product side of that reaction. So we'll go ahead and do example number 3. But again, it's pretty straightforward. You just remember that the coefficient tells you about the number of copies of a molecule you have. So let's go ahead and do the last problem we see on the screen. So this is going to be BaCl2 aqueous. Remember, that just means BaCl2 is dissolved in water in this case, plus Na2SO4, sodium sulfate, and that is also an aqueous solution. That is going to yield BaSO4 solid and 2NaCl, and that's aqueous. Kind of ran out of space on the screen there. But 2NaCl, that's aqueous. So, let's go ahead and first make a list of reactants versus products, the number of type, or the type of each atom, not necessarily the number yet. So let's make a list of the types of each atom we have. So in this case, if I'm looking through the reactants, I see barium, I see chlorine, I see sodium, I see sulfur, and I see oxygen. In my products, I see barium, I see sulfur, I see oxygen, I see sodium, and I see chlorine. So it looks like we have the same type of atoms on both sides if you're not catching a trend here. Remember the law of conservation of mass says we're neither creating nor destroying mass, so we're going to have the same number of types of each atom. So therefore, we'd have to have the same type of each atom. So let's go ahead and count the number of atoms in the reactant side of this chemical equation. So how many barium atoms do I have? It looks like there's just one BaCl2 molecule giving us one barium. If I look at chlorine, again, I just have one BaCl2, and chlorine has a subscript of 2, so I've got 2 chlorine atoms. Same thing goes for Na2SO4. There's only one of that molecule, so I'm getting all my sodium in the reactants from that molecule, so that means I have 2 Na, because I have Na2. So I've got 2 Na atoms. I have 1 sulfur atom and 4 oxygen atoms. Okay, so 1 barium, 2 chlorines, 2 sodiums, 1 sulfur, and 4 oxygens. In the products specifically, I'm going to go ahead and count those up next. So, barium is, it looks like I only have 1 barium sulfate molecule, so I've got 1 barium. I'm looking through, I only see that 1 sulfur in the SO4. I have 4 oxygens from my SO4. However, when I check this out, I see that I have 2 sodium chloride molecules. So if I have 2 sodium chloride molecules, that means that I'm getting 2 copies of sodium, 1 from each molecule. So I've got 2 sodiums, and then I'm getting 2 copies of chlorine, 1 from each atom. So this is going to be 2 chlorine atoms. So that's how you count the number of each type of atom you have in a chemical equation. Remember, eventually we're going to use this information to allow us to inform if a reaction's balanced or not. And then we'll go on to balancing the equations ourselves. So that's where we're going. Keep that in mind. I have left you with some practice as well. So here are some explanations about those. So please go ahead, work through those on your own as well. And then you can look at any chemical equation I have put in the slides for the next few days and start to try to count the number of atoms as some practice.